A. Describe briefly a projectile motion. So projectile motion is a parabola path in the xy plane due to constant horizontal speed of an object under influence of gravity. So this is the answer for this A, and this xy plane is just a graph y and this x, and the parabola shape is just like so. This is what will form when the projectile motion is happening. So now we can proceed to the marble of this B. A marble of a mass of 30 grams. This is M, and row of edge of the table will height 2.0 meter. This is the H, and strike the gap in the horizontal distance of 2.8 meter from the edge of the table. So horizontal distance, let's say is X. And so this is a situation. We have a marble at the edge of the table and one to row off. Now we have a table of the height. This is H is given by 2.0 meter. And when this thing reach a ground, have a horizontal distance 2.8 meter. This is X, and the first calculate the time taken by the marble to reach the floor. So this is B1, and this is given by y equals uyt plus 1 over 2at squared. And initially we don't have a y component, so this is 0, and this y we can substitute this h, and plus 1 over 2. This is acceleration, is just a gravitational acceleration, so 9.81, which is given by g. This is t squared, and we substitute this h 2.0 to 1 over 2, 9.81. And we solve for this t. So we get 0.639 seconds. And now the second question, determine the speed of a marble just before it falls. And so this just before it falls, so we want to find out this u here. Now we already have this time, so we just apply this u x equals to x per t. So actually this ux is also equals to u, because initially we don't have a y component, and so u equals to ux equals to x over t. We have x, which is 2.8, and the time t is 0.639, and here we get this 4.38 meter per second. Now calculate the magnitude of the magnitude and the direction of the velocity of a marble just before it reaches the floor. So in this case, we want to find out the velocity at here just before it reach the floor. Should be somewhere like so. And here we can see here have a y and x component, and we know that this ux will equals to v x, because this is a constant horizontal velocity, and the gravitational acceleration only in this y component. So now we have to figure out this Vy. Vy is given by V square U square. Of course, this is Uy for y component plus 2 GH, and this Uy is 0 as we as I said before, because do not have the initially do not have the y component for the velocity, so this is just substitute a number, like y at 1, and this is 2.0 y square, and we solve for this Vy. I get Vy is given by 6.26 meter per second, and now we can find this V, which is Vx square plus Vy square, and the 14 square root. Substitute the number 4.38 square, and this is 6.26 square. So it is 6.64 meter per second. And we also need the direction. So direction is given by delta equals to arctangent, which is Vy per Vx. So we just substitute the value 6.26, and this is 4.38. I get 5.02 degrees, and this is below the horizontal. Now finally, this last one, determine the average power of the marble. This is a 4 ratio 4, and this is given by the power is given by the energy per unit time, which this energy in our case is 1 over 2 mv square per t, and now we can just substitute the value, which is 313 and 10 to the negative 3, and V is 7.62 square, and T is from this V1 0.639. So I get the answer 1.37 watt. So this is for this question. 10a, state the characteristic of an electromagnetic wave. And the first is that there is a transverse wave, and the second is that does not require medium to propagate. And now B, the displacement y at the distance x and the time t of the sound wave propagate in the A can be represented by this, and where x and y are in meter and t is in second. So sketch on the same axis a graph of y against x as time t, equals 0, and t equals t per 4, where t is the period of the wave. Now, here we start drawing the graph. This is y and this is x. This is 0 point. And now we first substitute this t equals 0 inside here. And you can see here we'll have a negative in front at here. So that means actually if we draw this graph, right, we have to start from this lower part and going back. They will form this kind of shape. And the second part, t is equals to t per 4. So first thing we have to know this is a complete oscillation, and they will corresponding to the full period t. And now the time is given by t over 4. We only need a 1 over 4 part. From here, this is a 1 over 4, which corresponds to t over 4. And now we change the color for my pen. Now we start drawing from here, because they are going with this t over 4, and the rest we just repeat the same oscillation, something like this. And this is due to the t is equals to t over 4, and this is the path form. And for the blue line here, this is t equals to 0. Now the second, determine the velocity and the frequency of the wave. So velocity is given by f per lambda, and also given by omega k. And because this f is also equals to omega per 2 pi, and lambda is also equals to this 2 pi per k, you can substitute this 2 inside the equation here. You will get this final result. And now we have to find all the omega and k. For this case, we compare this equation to the standard wave formula, which is given by this omega t minus kx. You can see, you can compare this, we get our omega and we get our k, which is just substitute. So this is 300 meter per second. Now we have another task, frequency. We just apply this formula here. Find 2 pi I get 50.1 Hz. And now calculate the phase difference of the point 2.0 from the origin. So let's say this phase difference is given by phi, and this is given by x. Now again, we refer back to this diagram here, and you can see this is a one complete oscillation. That means they will be correspond to 1 lambda, and in terms of this radius, they are given by 2 pi, because this is a complete oscillation, one complete cycle. This is 2 pi radius. And so in this case, we can say lambda is proportional to 2 pi radius. And in terms of ratio, this lambda per x is equals to 2 pi per the phase difference. And so we have to find out the lambda first. Lambda is given by 2 pi k is 1.05. So we get this 5.98 meter. Now we substitute this thing inside here. This is 2.0, 2 pi, and this is a 5, 5. And I get this 2.10 radius. Now, yeah, we're done for this B3, and now describe the principle of the Doppler radar used by the police to determine the speed of an automobile. So first thing is that Doppler radar emits a radio wave of frequency f naught, and when the radio wave hit the moving automobile, wave with difference in frequency, let's say this time this is f, is reflected so by comparing frequency f naught and f, the speed the automobile can be determined. So this is basically the concept of this Doppler effect, but this is for the light. So technically for the light, the case will not be the same as the in the sounds. Actually, this for the light. If you want to do the formula, this is not inside the STPM series because you have to take consider of the special relativity, and this is not inside the STPM series. But for this case, we don't need to giving the formula and do the calculation. So I think this is still reasonable. If you are interested, you can take a look for the special relativity and you search for this Doppler effect for the EM wave for this electromagnetic wave. 11a, what is meant by work done in an isolated gas system? So the work done is the work is done by gas to expand the volume of gas without having the mass or heat transfer in that system. Here the keyword is this is without is mass and heat transfer. This is mean this is an isolated system. And now the second question, differentiate between the internal energy and the thermal energy of a gas system. For this, we start from the internal energy. Internal energy is a sum of total kinetic energy and the potential energy. This is how we define the internal energy. So you can see here have a word total. That means kinetic energy, they have a few different type of kinetic energy. For example, the transactional kinetic energy, we have rotational and also vibrational. This is all kind of kinetic energy. Well, this gas having. Oh, so here we have of this. And from here, this potential energy, we also have a different kind. So one of that is given by the attraction or repulsion between the gas molecule itself. So this is how we define the internal energy. And here we have another word called thermal energy. This thermal energy is just basically is the heat transfer. So thermal energy is the heat transfer between the gas and the surrounding. And now we have three. State the first law of thermodynamics and the meaning of each symbol used. So this is given by delta U is equals to this Q minus W. This delta U is internal energy, and this Q is the heat transfer, and this W is the work done. Actually, this is basically like the conservation of the energy. you can see here Q, this is heat transfer, is given by du plus W, and that means if we apply let's say the heat to the certain gas molecule, here they have two possibility. One is that they may have a change in this volume which given us the work done, and another possibility is the temperature of the gas increase, and so this is what contribute to the internal energy, which it increases the kinetic energy of this gas molecule. So you can see here this is basically the conservation law for the energy. This is what meant by this first law of thermodynamics. Be an isolated system with N 3.0 mole of ideal gas initially at a pressure P1 and a volume V1. It is then allowed to expand at a constant temperature T equals to 350 Kelvin to a new pressure P2 and a new volume V2, which is twice of the initial volume V1. So here we know that V2 is equals to 2V1, and we have a constant temperature. The first question, sketch the PV graph to show the expansion process, and the shaded area represent the work done during the process. And so this is a PV and this is a 0. And since here the work done is happening at this constant temperature, so work is given by this nRT ln V2 minus V1. And this work done is also given by the area under the graph. And here you can see that this is a long graph, and the nRT is just a constant, and so the graph will look something like this. And let's say here is the V1 and here is V2, and this shadowed area is what we call the work done, and here is correspond to the P1, and here until here will correspond to P2. So this is the answer for the B1, and now B2 calculate the work done during the process. So in case you are wonder, this work done is divided by the integral of this 1 or 2 and P dot dV, and this ideal gas law PV equals to nRT, so P is given by nRT V, and we substitute this inside here. From here, let's say we want V1 to V2, so P is nRT per V dV. If we integrate this, we will get nRT ln V2 per V1, which is the formula I write down here just to show you how to get from this fundamental equation. And now we can start calculate the work done. This is a 3.0, this is a 8.31, and temperature is constant 350 ln. This is remember this V2 is given by 2V1, so we have 2V1 per V1, so 3.01 350 ln 2. So I get 6048 joule, you can also write this 6.05 joule. The diagram below shows insulator windows of a glass of a hull which consists of two glass panels and separated by a layer of A. The area of the windows is 2.0 meter multiplied with 1.5 meter. This is the area A, and the thickness of the outer glass in the glass and a layer of 5.0 mm and 3.0 mm and 3.0 cm respectively. The temperature outside the house is 45 degrees and the temperature inside the house is kept at 20 degrees. Calculate the energy per hours this prevent from entering the windows. So I think I will start from this how to derive the equation used for this question. And so let's consider this. We have two layer 1 and layer 2, and here we have temperature 1. And at the middle here, this part we have a T, and finally until here we have a T2. And now the rate of heat flow is defined by dq dt, and I will use dot q to represent this. This is equals to k1a t1 minus t, and this is x1, and the x1 is given by the distance here. And now we also got this for the layer 2, this is k2a, this is t minus t2. You can see from here this is t, and we have to minus this from this temperature in internal temperature with this part, the t2 here. So this, and the distance from here to here is given by x2, so we have x2 here, and now we can write in terms of this t minus t2 is given by x2 k2a. This is dot q, and let's say this is a second question, and from here here we can write down this is t1 minus t is given by x1 k1a dot q. Now let's say this is a first equation, and if we 1 plus 2, you can see here is a minus t, here is a t, so these two, the end our result will give us a 0. The thing left is t1 minus t2 is equals to x1 k1a and plus x2 k2a, and this whole thing multiply with the dot q, and so dot q is given by t1 minus t2. This is x1 k1a plus x2 k2a, and by using the same logic we can get a general equation which is t1 minus t2, and this below here is denominator here is xi kia, and I think you can see the logic here, and this I is given by any integer which depends how many layer you have, and in our case we have a 3 layer. This is 1, 2 and 3, and so for us is the same formula, and we can write down this is x1 and kg. For this g, actually I refer to this thermal conductivity of the glass. This is what I call the kg, and this is area plus this is x2 This is a Ka. This A is referred to the A here, so the Ka is this guy here, and this is A for area. This is the X3. We have a Kg because you can see the layer 3 here is also made out of this glass. So this is A. And this x1 is just given by the distance for this layer 1, and this is x2 for the layer 2 and x3 here for layer 3. You can see the denominator here, kga is the same for this and this. So in terms of equation, we can write x1 plus x3 per kga plus x2 per kaa. Okay, now we can substitute the value inside. The T1 is the outside the house, which is given by 45 and degrees, and the T2 is the inside, this is given by 20 degrees. So from here we want to find out x1. X1 is 5.0 plus s2 3.0, and this is a 10 to the negative 3 to convert it into the meters, and kg is given by 0.84. The area is just 2.0 multiplied with 1.5. Now we have to plus this x2. X2 is given by 3.0, 10 to the negative 2, and 0.023. Area is the same. So I get a 57.1 watt. Here the question requires us to give the energy per hours, and as we know this watt is the joule per second, right? So we have to convert this unit into the joule per hours, which can be done by multiply with this P600. And if we do this, so 600, and I get 2.056 10 to the power of 5 joule per hours. Yep, I think this is the final answer. Is state two function of a dielectric in a capacitor. So the first one is to increase the capacitance, and the capacity is given by C equals epsilon A per D, and you can see here when this dielectric is used, the epsilon will increase, and so this C will also increase, which this is one of the function for the dielectric. And the second is to separate the charge. And now B, a pure capacitor of a capacitance C1 5 microfarad, and the C2 10 microfarad are connected in a series to the 10 watt battery. So this is 10 watt is V, and now derive a expression for the effective capacitance CT of a circuit and calculate the value of a CT. So this is B1. So first thing first, let's take a look at this circuit. This is a connect in series, so we have a C1 and we have a C2. We connect to the voltage supply, and here the positive will have a current flow through here and charge out the capacitor here, this part to be a positive, and the electron will get attracted to this part as an equal amount, and so this will form the positive here, and again the same thing, the electron will get attracted in this side, and then here become a negative charge. Now we can conclude that this Q is the same for this C1 and C2. And now let's say we have a voltage across C1, V1, and voltage across C2. This is V2, which provided by this V. So V will equals to V1 plus V2, and Q is equals to CV, and this V will equal to Q plus C. We substitute inside this case cube CT is equals to cube C1 plus cube C2. So CT is equals to 1 over C1 plus 1 over C2 to the negative 1. And this is the expression for the effective capacitance. Now they want us to calculate the value of CT. So here CT is equals to 1 over C1, so it's 5 over 0, 10 to the negative 6 plus 1 over this 10 negative 6. We can get 1 over 5. So I get a 3.33 10 to the negative 6 farad. And the second part, calculate the total energy stored in the circuit. So the total energy is given by 1 over 2 CV square, and of course this C is CT. This is 1 over 2 CT, 3.33 10 to the negative 6, and the voltage is given by 10 for the battery square, which 1 over 2, 3.33 10 to the negative 6, and 10 square, I get 1.67 10 to the negative 4 joule. And just in case how do you want to know how to derive this formula here, this is from this U is equal to integrate du, and remember that this du is given by QV, the charge multiplied with the potential difference. So du is equals to the V dq. So we get V dq, and now you have to integrate. Let's say we want to 0 to go to the charge of the Q, and here you can see this V is equals to Q plus C. We substitute this inside Q plus C dq, and after integration we get a Q squared plus 2C, and now we make this Q in term, we substitute this Q to CV, you will get 1 over 2 CV squared. This is how we derive this formula. So C, battery in B is replaced by the alternative current of the supply of maximum voltage 10 watt. This is V naught, and with a frequency 120 Hz. This is a frequency F. Calculate the reactant of the combined capacitor. So first thing I want to write down is a CT from just now we calculate 3.3310 to the negative 6 farad, and here is the reactant is given by the xc is equal to 1 over omega c is given to 1 over 2 pi fc, which is 2 pi f120 and 3.3310 to the negative 6. So 1 over 2 pi 120 3.3310 to the negative 6, and we get a 398.3 ohms. So calculate the maximum currents in the circuit and comment on the phase of the currents with the reference to the voltage supply. So here V is equals to I xc. In our case, we want the maximum, so V naught is equals to I naught xc, and this is basically the Ohm's law, which V equals to IR, and but in the alternative current, this I is replaced by this xc. In this case, actually it can be others like the Z or the XL, but in this case we only consider capacitor, so we use XC. So we have a 10 watt, and we have I know, and XC, this is 398.3, this is I know. So we get 0.0251 ampere. Now comment on the phase of the currents with reference to the voltage supply. So in this case, this currents where the voltage by 90 degrees. So the third, describe briefly the behavior of energy stored in a combined capacitor during a cycle of alternating current supply. So here, this is let's say this is I, this is T, this is 0, and we have a full cycle. And this will be the T1 complete cycle by definition. This is a period, and here is T over 2, and here is T over 4, and finally here is T over 4. So from here we can see this from 0 to T over 4. This will give us the currents is 4 into the capacitor. So energy stored increases, and the second part, this T over 4 going to the T over 2. In this case, the currents is for up from the capacitor, right? And so the energy store decreases, and now this T over 2 to 3T per 4 is same as this 0 to T over 4. But in opposite polarity, and you can see from here this is this part is below here, which opposite of this when this 0 to T over 4, this is what we call the opposite polarity. So at the first place is this is at the first place, let's say from 0 to T over 4 is charged out this plus, and here is minus. So when the now this T over 2 to 3T over 4, they will charge out this part with negative, and this part to be positive. This is what we call as a opposite polarity. And finally, this 3 over 4 to this T will give us the same as this T over 4 to T over 2, but in opposite polarity. But of course, in terms of the energy store, they will still be the same. In this case, we don't really care about the polarity of the currents. Just this I write down here is just some addition knowledge maybe you would like to know for the currents, and this is basically the answer. Study both free hypothesis and give a relationship between a momentum p and the wavelength lambda of a particle. So in this case, we get a mass with velocity will have a wave properties which the wavelength is given by lambda equals h per p, and this h is a Planck constant and p is just the momentum instead here. Now B, in an electron diffraction experiment, an electron beam which is accelerated on a potential difference is indicated normally on a very thin gold film, and several circular diffraction beams are seen on the photographic film. And if the voltage of an anode is increases, what happened to the circular rings? So this is a B1. So when the voltage increases, the wavelength decreases, and the radius of the ring decreases to now B2, if a particular ring of a radius R is chosen and different values of accelerating voltage V are recorded, sketch a graph of R against 1 over square root V. Deduce the experiment is in agree with the de hypothesis. So first thing I think we better do a diagram first. This is an electron gun and shoot our electron beam and hit the target metal. In our case, it's a gold film. And behind here, we'll have a screen. This is what the question called as the photographic film. So here, when hitting this goal here, they will have an electron diffract out, like something like so. Let's draw it bigger and something like so. And you will observe a circular ring on the front here. Now let's say this is the center of the ring. We can draw a triangle from here to here, and this angle here will given us by 2 data. So let's draw a 2-dimensional one to looking better. This is electron gun and we have electron beams, and this is the gold film. And behind here have a photographic film. So, and when this electron hit this gold film, they will diffract out. Of course, we only focus on one particular ring in our case here, and here is 2 data, and here of course is given by this will given by R, so here is given by R, and let's say here is X. So now we start from this finding the lambda relationship between the lambda and the voltage first. Lambda is given by h per mv. This mv is just a momentum, and we use the energy approach. 1 over mv squared equals to ev, and v is equal to square root 2 ev per m. Good. And we substitute this v inside here, we get a h per square root 2 evm. Now from here we get our lambda. Now we have to find a way to relate this lambda with the radius r. So since this is a diffraction, right? Diffraction, the formula is given by m lambda equals to 2d sine theta. When the data is very small, this is approximate equals to the sine data, so we can write this 2 data, and this is also approximate to the tangent, and In our case, we can write down like this. Two data is approximate tangent two data, and you can see here this tangent two data is given by this. This is R. R is opposite, and this is adjacent. This is a definition for the tangent, which in our case is R over X. So we substitute this inside, we get this d R over X, and we use the lambda we substitute this thing here inside the n lambda, we get h square root 2 EVM. So you can see this is quite clear. This R will be proportional to 1 over square root V. Since this is a particular ring, this n is constant and h is a Planck constant, and the rest 2e and mass of electron, and of course this d and x, the rest is constant. You can see this is a proportional relationship, so the graph will look something like this. This is R and 1 over square root V. So this is a linear proportion. So this is our answer for part B2, and I want to mention more than that. When we at the part B1, we state this when the voltage increases, the wavelength decreases, and this can be explained by this equation here. You can see clearly this is when this voltage increases, this lambda will decrease, and next you can see this is here we start to rewrite this voltage and this radius here, and as you can see from this formula, this is also the R is decreases when the V is increases. So in our case, the voltage is increases, so the radius decreases. So this is consistent with the formula we derived here. This is basically the explanation for the part B1. Now finally, you can see this is agree with the Boris hypothesis. So here is the answer for B. Now we go to the part C1. We have a 60 kg marathon runner run at the speed of 5.1 meter per second. This is velocity v. Calculate the de Broglie wavelength of a marathon runner. So we apply the formula we used before. Lambda equal h per mv, and this h is a Planck constant given by 6.63 10 to the negative 34, and now mass is 16 and 5.1. I get 2.17 10 to the negative 36 meter. Now explain briefly the production of a continuous and a characteristic with X-ray. And for the continuous X-ray are produced when the fast moving electron hitting the target metal, the loss of the kinetic energy is converted to the X-ray energy. This is for the production of a continuous X-ray. So we have another what we call the characteristic wavelength X-ray. So for this characteristic X-ray are produced when the electron in the cell get knocked out by the incoming electron that vacancy when that vacancy are being filled by another electron, the characteristic X-ray are produced. So the keyword here is this the electron in the cell get knocked out, and the second is that vacancy are being filled. This is how to produce this characteristic X-ray. A1 define a neutron number and a proton number. So neutron number is a sum of the proton and neutrons. Sometimes this is also known as this mass number. And now a proton number is just a number of proton in atomic nucleus. And now A2, what are isotope? So isotope is the substance that have same number of proton but different number of the neutron. So here B, the diagram below shows a schematic model of a mass spectrometer. And ion enter the velocity selector with the electric field E and magnetic field V1. The velocity of the ion of a charge Q at the slide S is V. The ion then enters the region of a magnetic field B where it is diffracted in a circular path of a radius r. So express a V in terms of E and V1. So in this case, you look at this region, you can see the ion still going in the straight line. That means the force must be balanced out by this magnetic field force and the electric field force. So here magnetic force is given by B Q V, and this is a B1 in this region you can see here, and is equals to the QE. Now we cancel out this QV, we will get a E per B1. So this is the answer for B1. Now this is B2, derive an expression for the mass of ion in terms of E, B1, B2, R, and Q. So from B1 we derive that this is V is equals to E per B1, and now for this B2 we were going to use this. First thing, when here the particle here at this turning path here, they will experience a centripetal force which is given by the mv squared per r, and this must be equals to the magnetic force. This is due to this B2. So this is given by B2 QV, and this is a centripetal force, and this is a magnetic force due to B2. And now we have a mass here, we make it in terms of other thing. This is this V can be cancelled out, so we get B2Q R per V, and we substitute this V equals E per B1, we will get B1 B2 QR per E. Yep, I think this is our answer for this B2. Now For B3, if B1 equals B2 equals 0.01 Tesla and the radius in PCM, calculate the difference electric field to enable the mass spectrometer to differentiate slightly charged copper isotope and these two type of the isotope. So in this case, we use this formula. So we get E is equal to B1 B2 QR per M. Now let's say this is copper 63. This is we have this 0.01 square because this is a B1 and B2 is the same, and the charge given by 1.6 10 to the negative 19, and this radius is 20 10 to the negative 2 and divided by the mass. The mass here is given by in terms of U, but we have to convert it in terms of the kg. So we multiply this with 1.6 10 to the negative 27. I get 30.63 Newton per Coulomb. And now we calculate for the another copper 65 Cu, and again the same thing, just substitute the mass to be different. So this time is given by 64.927794. Again, convert to this kg. I get 49.7 Newton per Coulomb. So yeah, this is the answer for the B3. So this is a C1. Why does the fusion reaction take place at high temperature? So at high temperature, large amount of thermal energy are provided to the nuclide, and which able to overcome the repulsive force between each other. This is the answer for C1. And C2, calculate the energy released in the following fusion reaction. So in this case, this formula of the reaction is given, and we can add a final product here with a certain energy E. But of course, here is given by mass, so we have to make this all in terms of this mass. But basically, it's the concept of the conservation of energy. So in this case, the E should be divided by the C squared, and this is what we call the difference in mass. So this delta M is given by the mass of the Cu plus the mass of the H minus the mass of the N. Now we substitute the value inside 13.003355 plus 1.007825 minus 1.14.003074. So I get the 8.106 10 to the negative 3, and this is in terms of U, and we want the energy release, so E is given by delta mc square, and we substitute this M, and we multiply with the 934. This allows us to convert it into the mega electron volt. So we get the 7.57 mega electron volt. Now D, explain briefly control the fusion reaction in the nuclear reactor. So in the nuclear reactor, we have two things, two key points. One is the moderator. So in this case, we use water. You can also use the graphite. In this case, I use water. Water is used as moderator. To slow down the speed of the neutron. And the second thing is what we call the control loop. In this case, control root make out of control root made out of boron. Used to absorb the neutron which enable us to control of the rate of reaction. So the key point here is mention the system used for this moderator and the system used for the control rod and their function, which slow down the neutron and absorb the neutron. This few is a key point. This is the answer for D.